about zero-point energy, some of its history, as well as some current research that he's conducting. So without further ado, let's welcome Thorsten Ludwig.
Absolutely. Good to see you. Thank you very much. All right. So thank you very much for the organizers to organize this nice conference and for inviting me. Actually, exactly 10 years ago, we made a very similar, very big conference in Berlin that got us started into doing what we're doing today. So my specialty is zero-point energy. It's a little bit similar to what Morey told you, but I'm always surprised to see his presentation and then see that pretty much all my slides are totally different than his slides. So let's see if this works. Yeah. Okay, so the title of the talk was the sea of energy that we live in, and that's like the main point I want to get across, that there's a lot of scientific and experimental and technology evidence that we actually are surrounded by a lot of energy and that we can use that. So here we see some heroes. That's Tesla up there, and down there is Morey. So they both emphasize this, this point of a sea of energy that we live in. Actually, they were not the first ones. Like if you go into ancient India and other places, even still the Greeks, they had 5 elements, not just 4, and the 5th was space, was energy that surrounds us. So, but then it got lost as we moved into Europe. So this is actually the very modern viewpoint of physics, that we are, these are the vacuum fluctuations that were said. Some people call it the vacuum state. But basically, it's a sea of energy of, in this case, light, photons, or electric fields on the left that surround us, that fill the space. And we will learn in what I have to say, what are the fundamental historic and experimental facts that support this viewpoint. So here's a book of T. Henry Morey, Sea of Energy That We Live In, very interesting book. And he came out with a very interesting device that I brought out about 30 kilowatt. And a lot of people witnessed his demonstrations. One of the key things is a tube, a very special tube. And, well, there was no input power, and he somehow managed to light up all these bulbs and to produce 30 kilowatts. A lot of people in his time, that was the 1930s, a lot of people witnessed it. It's one of a long story where it got lost and why we don't have it as devices. Maybe at the end of the talk, I can a little bit go into the social surroundings, why it didn't happen, that we have it today. This is a very famous quote from Nikola Tesla. Here he says, "Before many generations pass, our machinery will be driven by a power obtainable at any point of the universe. Throughout space, there is energy. This energy is kinetic, and so it is a mere question of time when men will succeed in attaching their machinery to the very wheelwork of nature." So I haven't seen many slides on Tesla yet, so I want to give you a little bit of an insight who he was. This is the famous Wardenclyffe Tower, but this is 1893 in Chicago. He developed the AC current, the 3-phase that we still use today. He empowered all these lights here. He invented many, many things, and he wanted to go on and build this Wardenclyffe Tower. But actually, similar to the times we are in today, there were some financial problems at that time, and so he he couldn't finish it, and some people say it was suppression, but there are very interesting other stories that actually he got a certain amount of money, $100,000, but the value of the money devaluated during the project, and then he asked for more. It wasn't promised, and he didn't get it, so he wasn't too diplomatic. And so there are different stories on how and why this project wasn't finished. But as you can see, the mere size of it, it was a full-size project and very serious what he was doing. And we still use the AC today, so maybe we can move on to his wireless power in time to come. So for me as a scientist, this is very interesting because this is in Colorado Springs, and that's where he discovered this transmission that he built then in the Wardenclyffe Tower. Here he analyzed what's happening during thunderstorms, and then the Schumann resonances, the electric vibrations of the earth get excited, and he discovered that you can actually gain energy if you let power go through the atmosphere. So with this device here, the big shed, he discovered the secrets. So today there were also secrets. Up to maybe 10 years ago, people were wondering, how does the gecko stick to the wall? I don't know, many of you probably have been to Asia, and these little animals that crawl on the walls and the ceilings, and people were wondering, how do they do it? In this case, this big gecko here is walking on a glass, on pure glass. So there's no way he can hook to anything. It's very smooth. So how does he do it? And why am I showing you this? Because I personally am convinced if this free energy is real, then nature will be using it all the time already. And I think also we in our body will use it, but that's a different story here. This is bionics. It's watching nature, learning from nature. So in this case, the gecko actually is using, there are no hooks. If you look at the gecko, it's just a lot of hairs with a flat end. And we will learn in the course of the talk that that's a Casimir regime. It was a Dutch scientist who discovered that from these vacuum fluctuations, from the sea of energy, you can actually derive a force, which is called the Casimir force today. And the gecko in his feet is actually using the fact that if you have a large number of small, flat ends, and you stick them to a wall, you can have a lot of force. And that's how he is sticking to the wall. And then he just needs a technique to kind of roll his feet away from the wall to actually get it off the wall. Because he can, with his feet, and you can see here other insects are using the same thing, but the bigger the animal is, the more and smaller hair he needs to actually stick to the wall. So like a fly or something, they need much less hairs. So, and here on the right you can see bionic, you can see like a man-made structure which is doing the same thing. You can buy these things now. So we already went through the introduction into the topic, into the sea of energy. We will go on more into the physics, into the van der Waals force, into quantum theory, which is pretty heavy stuff, and I will kind of overload you with a few formulas, so don't be scared too much. Yeah. So, but I do that to show you that the zero-point energy is actually very integrated into the modern framework of physics. It's not something unusual or something on the side. It is actually very much embedded into the framework of physics. We will learn about experiments that kind of show that this stuff is real. Okay, like that. Hope the sound is better like that. And at the end, we will see what can we do to actually utilize this energy and what are the technologies that are out there today that probably use this zero-point energy. So the van der Waals force, also discovered, I think, somewhere in Holland. 120 years ago, van der Waals, he saw that in gas, neutral atoms actually kind of attract each other, and he didn't know why, and he found out why, and it called the dancing charges called of technique, kind of induced from the vacuum fluctuations. One atom kind of jitters, and it induces an electrostatic jitter into another atom, and that kind of attracts the two atoms towards each other. And that's the van der Waals force. That's why neutral gases kind of hold together, and it's a very, very important widespread chemical force. And so Casimir, which I already mentioned, he was studying van der Waals forces like 50 years later and discovered some unexplainable aspects of it, and that's why he derived his theory from it. So let's move on. So in 1873, so quite before quantum mechanics and other modern physics, van der Waals found out the points I was just making, and then only much later people could explain what was actually happening. And only in the 1950s people really understood how the van der Waals forces actually come from the vacuum fluctuations, and that they're actually the same as the Casimir force, which we will learn later. Very important part in physics to understand this whole topic is quantum mechanics. So in 1900, in 1900 here in Berlin, Planck made a speech. He kind of first phrased that energy could be not continuous, but in chunks, in quantums. And from that, he could explain black radiation, meaning heat radiation that wasn't explainable before. And so the whole quantum mechanics came along, and here the name Nernst, he actually was the one who kind of took this concept of quantums to the next level, that also space itself, the energy in space needs to be quantized, called the second quantization. And it's a very important part in developing the zero-point energy concept. And what Maury also mentioned already is this uncertainty principle from Heisenberg. So let's see if we get this laser pointer going. No. Okay. Anyhow, you see the one formula there, and you see that the uncertainty of position and inertia is kind of uncertain. So, but the same applies to other values, and in this case, time and energy also is uncertain. And from this uncertainty comes the point that energy can exist for a small amount of time, like for example, a green photon can exist for 10 to the power minus 21 seconds. And so a virtual photon can just come into being, live for this short amount, and then kind of vanish again. And this is exactly the same concept as the vacuum fluctuations, because a photon is also just a vibrating electric field. So this can come into being and go away. So these are just different descriptions of the same thing. Now, these people are important because in just after the Second World War, 1945 to 1950s, the quantum field theory, so the quantum theory of space itself was developed. And people like Schwinger, who got the Nobel Prize for this, they found out how these electric fields, how these fluctuations, how that works. They came up with the formulas and how to calculate this. And then Hendrik Casimir, who was working for Philips in Holland, he discovered that you can use that to create a force. So this is again back to the basic principle. You see something, a harmonic oscillator, or a physicist would say a system. So in this case, the electron on a spring means a force field. In classical viewpoint, it can stand still. It can have no energy at all. at one point. But with quantum mechanics, is something that Morey also mentioned, you cannot have that. At the end, you still have the 0-point energy. There is no standing still. It's the same thing at this energy time uncertainty. It means there is this jitter at the 0 point. 0 point meaning zero temperature in this case. So, and if you apply that to the right side, you apply it to that rectangular cavity, means to space itself, just empty space, vacuum or any space, and you still have possible electric fields, and also these possible electric fields, like light or whatever, they cannot stand still. They also have like a minimum, but you can also look at it from a statistical point of view, fields coming into being and going out of being, which is this jitter. So here you see some field modes, some possible vibrations in empty space, and these electric fields, they are not zero. Each of these modes, meaning possible vibrations, always has this jitter, yeah? So, and if the left side of this slide here, you can see that you can calculate over all space and all possible vibrations, and then you can come up with a number. And please note that the omega here, meaning the frequency, it goes with the third power of the frequency. So it really goes up when the frequencies go high. So the most of the energy is in the high frequency part of these vibrations. And this will become important if we apply this to kind of understand how can you use it. So it means very small space and very high vibration. That's where the energy is. In the low and slow parts, there's not so much of this energy. So here you can see these are Feynman diagrams, and maybe not all of you can read them, but basically you can see like the upper left one, you can see electron coming in and going out. Okay, like you can read from the bottom to the top, and from left to right is time. Time is from bottom up, and space is left to right. I have no time to go into full detail of this, but the thing is, these are the four fundamental interactions, the main forces. So, and in physics, if you have a line here which starts outside, like the electron here, and goes out, that's a real particle which keeps on existing. But the photon in the middle, which is kind of starting and ending in the graph, is called the virtual photon because it's like this vacuum fluctuation. It comes into being and it goes away, and it lives for a short time. But this virtual photon kind of transmits the electric force. This is standard physics viewpoint. So I show this graph to show you that these virtual photons, they're not some side effect. In modern physics, they are the fundamental what holds everything together, are these vibrations in space. Because in modern physics, people don't think in fields, like electric field, which is just everywhere, because you can easily calculate that it would violate energy conservation law if something is everywhere and very strong. So they do this via these virtual photons. And there's a big mathematical framework called quantum field theory where you can calculate all this. And it's especially important, going to this graph, if you go into high energy physics and these colliders like in CERN, they need to do all these calculations to really understand what are these particles and what is happening. And this is from Feynman lectures, a very simple thing. You can see here how it works. Time is on one side of the graph and space on the other. And you can see like it shows a proton and an electron. This is just the atom in this Feynman diagram, and it shows how the electron is bound to the proton via these virtual photons. And you can see that in some of the virtual photons, there's like a little circle with some arrows, these are actually the pair production. Really, these are called higher orders, okay? So with these called the radiation correction, you can make all sorts of calculations of effects that, like the lamp shift and other effects that were not explainable if you do not take quantum field theory into account. If you just do the basic things, you cannot explain quite a few things. So this is a list of experimental evidence for zero-point energy. The lamp shift is a little shift in the hydrogen spectrum. So the energy levels of the hydrogen atom, if you apply what I just said with these higher orders, you can calculate that the energy is shifted a little bit, and you can very precisely calculate the energy of the hydrogen levels. The Casimir effect, I will talk quite a bit more in this talk about. The electron charge and vacuum fluctuations is if you, in space, and that's something that Maury also said, is that electrons and positrons, they come into being and destroy themselves in a very short period of time. That's called vacuum polarization. If you have a charge, like the electron charge, and kind of separate these electrons and positrons while they are in their small lifetime. And that actually changes the electron charge. And if you collide two electrons, they did that in Japan, for example, then you can kind of measure how these kind of dive into the cloud of vacuum polarization around each other. So these are examples where you can see that these theories that I was glancing at in this talk have a very strong experimental evidence. And it was actually the lamp shift that triggered the quantum field theory. Because of the lamp shift, people started to think, how could we explain this? And they found that if you take these vacuum fluctuations, this radiation background into account and do the calculations, then you can actually calculate exactly the lamp shift. So now we come to the Casimir force. I emphasize this because this shows that you can convert the vacuum fluctuations, or the sea of energy as you like, into force, into something usable. And how does it work? Well, you see these plates here are metal plates, and on the right side and the left side of the plates there's a lot of space, so you can have longer electrical vibrations, while in the middle, the very long ones are restricted. They don't fit inside, okay? So they cannot be there. You have less frequencies, less modes. So if you do the calculations, you can see that the virtual photons, they put like a photon pressure on the plates, and there's more from the outside than from the inside. So the plates are pushed together. And this was discovered here in Holland in the Philips labs in 1947, theoretically by Hendrik Casimir. And here you see the same thing. Here you can see a little bit more clearly that the long vibrations don't fit between the plates and the force. So the force gets larger if d, the separation of the plates, gets smaller and smaller. This is a book I recommend, which shows all this, and it also emphasizes how the Casimir and the van der Waals force, these so-called dancing charges, which I mentioned in the beginning, they're actually the same thing. They're just different viewpoints. While van der Waals kind of looked at dielectrics, Casimir was looking at metals, and you have to do a little bit of a different mathematics to find that out, but it's in principle the exactly same thing. That's the modern viewpoint. So it took, I think, 70 years after the discovery of the van der Waals forces to actually see that it's the same thing. So we have this here. This is another nice picture of the gecko feet. You can see how you have so many very, very small hairs, and the hairs are flat, and he sticks it to the wall, and all these flat places, they kind of do this Casimir force, and that's why he can stick anywhere to the ceiling and walls. So, and you can see here 2005, it's pretty recent that people found that out. Before they were just wondering how this works. So now we move to the next phase. Now I'll show you a little bit how the Casimir effect is measured today. And that leads also to research how to use it for little machines. And it all goes into the so-called nano world, the nano machines, nanotechnology. And there are two different ways, modern ways, how to do it. One is based on the atomic force microscope, and the other is based on so-called tuning forks. Like every one of you who has a digital watch, a quartz watch, you will have one of those quartz tuning forks inside them. So, well, this is the idea of the atomic force microscope, which was discovered in the 90s. And with that, you can actually, you have a small tip, which is only like 1 atom large, and you kind of scrape it over a surface, and then you measure with a laser beam the flexion of the cantilever, and then you get a signal which is related to the surface, and you can make pictures of nanosurfaces. You can have a resolution up to 1 nanometer quite easily, and it's very widely used in laboratories today because it's very simple. You can put it on any surface, and very quickly you can make a picture of it. So there are other ways of measuring the Casimir force. Here you can see they use a ball, and this is called the MEMS device, a microelectronic device. This little blue thing is only like a few micrometers large, and it's like a little balance, you know. And the gold plates, the yellow plates on the bottom, like with the capacity of that area, you can then measure the distance, and by that way you can see here all the details of it. You can measure the Casimir force with this very, very, very precisely. So here you can see the real device, how it looks like. It's kind of etched from the full metal. So there are lots of details which I'm not going to go too much into. The main difference to the atomic force microscope is that was static. You kind of let the cantilever go down, and then you measure the force directly. But in this case, you let the whole thing vibrate. You let it oscillate on its resonance frequency, and then you can see a shift in frequency, and then you can measure the force by that. Here you can see it's quite important, the roughness of the materials, because we kind of want to bring the ball next to the flat area in, let's say, 10 nanometers, 50 nanometers, and if your roughness is 50 nanometers, which is actually optically flat. If you have the feeling it's super flat, it's like 50 nanometers flat, the roughness. So you have to go beyond that to go closer. And that affects the whole thing. You will see in a little while I'm going into these details of roughness and so, because if we actually want to make machines, these things become important. And so here you can see the pictures usually taken with an atomic force microscope here on the roughness. Well, this goes into another way. This is now the quartz tuning forks, which what I personally like about it is, let's see here, these tuning forks you can buy for like 70 cents, you know, but then you can make a device out of it where you have a atomic resolution, you know, like 1 nanometer resolution out of a 70 cents device. I kind of like this. So anyhow, you have to put in a lot of work to get this doing. So here is one, again, the cantilever thing. Why do we use a sphere and a flat? Well, the thing is, people found out that it's very difficult to have two flat surfaces and bring them very close to each other. The alignment is a big problem, so it's much easier to use a sphere. You don't have to align it. Any way you approach it to the flat area, you will always get a very small separation. And so all the people I know who are successful in measuring the Casimir force have done it with a sphere and a flat. Some Italians, they are still trying to use a flat arrangement, which gives you more power. You kind of lose one dimension. You lose like 7 orders of magnitude in your force if you do this, but still it's easier and people do it like this. Here you can see a picture from my lab where I did this. Here is this watch and this tuning fork in this watch. So what I do is I cut open this cylinder and then I get out these tuning forks, and if you let them vibrate and you can measure a force in the region of piconewton with it as a change in frequency, because they're very, very precise, very sharp resonance. So that's why it's possible. And here you see somebody who made atomic resolution with the quartz tuning fork setup. So it's there are a few reasons why this is better. Actually, very practically, if you use the cantilever, the silicon cantilever, it's more easy because you directly measure the force and you can buy the equipment more readily. But this cantilever is too soft. If you come to the flat surface, usually what happens is it goes bang. It's drawn to the surface, so you cannot really keep a close distance because the force gets too large and the ball just sticks to the flat, and then you kind of have to bend it back and break off the cantilever. And so if you use the tuning fork, it's much more stiff, so you can approach closer, and that's why it's working. Here you can see the physics, how you can actually measure a force by changing a frequency. I'm not going too much into the details of it, but here you can see the different vibration modes of and here up there you can see the basic setup. You bring the tuning fork close to your sphere, then you have again this Casimir regime, this force, and the force will change your frequency a little bit, and you can measure that here. You can either use the phase shift or you can use the change in amplitude of your force. Here is some pictures from my lab where I actually did this, and here's some more details on how you calculate the stiffness, the K. And this is my atomic force microscope where I do these experiments with. It's a setup where I can evacuate everything, so it's more precise than doing it in air. So this is all from the lab, the setup there. Yeah.
What force are you actually measuring?
Well, the Casimir force. Earlier,
That's a homemade force in a way. What kind of a physical force are you measuring?
well, I don't get your point.
What is it good for in a way?
Well, we will see that. Earlier I explained that the Casimir force is kind of coming from the sea of energy. It's coming from the quantum field and these fluctuations. If you restrain them by actually limiting the space for the electric vibrations, then a force comes out of it. Okay, and that's the Casimir force. And,
It's a force.
Please continue your presentation.
Okay, thank you. I can explain to you later, okay? So anyhow, this is the setup with which I measure that. Here is another setup. So if you have the quartz tuning fork, this is actually how you can measure the frequency change. You excite your tuning fork very precisely on a certain frequency. You use a lock-in amplifier, and then with a computer, you can scan through the different frequencies and kind of see where the amplitude is higher and lower, and if you see a shift, then you can calculate the force from that. So some more pictures on how it's actually done and the equipment used. And this is what I was saying, that it's a very sharp resonance. And here the resonance was measured. And you can see that it's 316 millihertz on a 32 kilohertz signal, which means that the quality of the resonance is 1 million. So you can see that the resonance is very sharp, and if it's so sharp, then you can measure a very small force that's connected. So here we again go into the roughness of the materials used, because we have the ball which is coated with gold, and you have the other surface, and it's important how the roughness is. We will soon do some calculations on how much energy can we actually derive in a Casimir regime, yeah? And it's important how close we can get the metals or whatever objects together. So, well, this is some notes on these experiments that I did, and I can report that both ways of using the silicon cantilever and also the Casimir force measuring by the quartz tuning fork, both is possible. They have their pros and cons, and don't think it's so important here to emphasize, which I already said, the stiffness, which is a very important part of it. So why am I doing this, you might ask? And I think in studying this, I'm using it as a sensor to kind of see if by any means we can make a difference in the zero-point energy. Because if we have a difference, if we have an area with more and a difference with less zero-point energy, then it's like having different pressures in water, you know. Then we can make devices or machines out of it, or can understand how free energy technologies, machines that we will see in a little while here in my presentation, how they can actually be understood with this quantum field theory concept. Another thing that I lately work on, which I want to emphasize here, is the connection between quantum field theory and magnetism, and also permanent magnetism. And the thing is, if you go into the quantum theory, after the basic quantum theory that I showed you a few things about, there comes the relativistic quantum theory. If you take Einstein's quantum theories into account, you have to kind of modify the very simple Schrödinger quantum mechanics and come to the so-called Dirac equation. And if you do that, then you can actually calculate that the electron needs to have a spin. And this spin of the electron, yeah, is actually connected to the magnetic moment, the magnetic force field of the electron. And in modern viewpoint of physics, we think that a permanent magnet, like a ferromagnet, is actually an alignment of many spins of electrons. So here on this slide, you can see that there is, in this formula, there is a connection between the spin of the electron and its magnetic moment. But the thing is, if you do the calculations and you do it a little bit classical, you will come that the G there, the little g, should be 1. But if we do the measurement, it's 2 point and then something. So 2.023 and so on. So with the Dirac equation, I'm not sure if I have it on the next slide, with the Dirac equation, you can actually derive that it's 2. But in reality, if we measure it, and Demelt, he measured a single electron in a trap, and he found out that it's the number that I showed you here. So the rest can be explained and calculated with quantum field theory, meaning the interaction with the radiation field, with these virtual particles, with these fields that we call zero-point energy, that actually shifts that magnetic moment to the value that you see here. And you can calculate that. For physicists, this is important. If you can have an experiment and then you have a very large, big theory and you can calculate exactly the number on many digits, it kind of gives confirmation that, yeah, we can actually do something with it and that it's a valid theory. And for us here, I think it's important to understand that any magnetic motor or so forth, there is a very deep connection between magnetism and zero-point energy. So, yeah, go ahead and build a magnetic motor. It's possible to draw this energy just using spins of electrons and permanent magnets. So here's like a graphic description of what I was talking about for those who like pictures more than formulas. Here you can see the electron, the ball with a spin, it's turning, it's making a magnetic moment. You can see if you align many of the spins, you can have a permanent magnetism. It's connected to this zero-point energy, this photon force field, and on the right you can see the Feynman diagrams that you can use to actually do the calculations and back this all up. All these pictures together, if you calculate them, then you come to this magnetic moment of the electron that I was explaining. So, I already stressed why I think it's important. I like magnetic motors. I think it's a great concept, and I think with this, arguments that I brought here, you can understand that it's very valid and connected to modern physics, that you can use these magnetic motors and so forth, and they could be actually harnessing zero-point energy. So now we are slowly coming to the last phase of the talk, and here you can see this is actually from Fabrizio Pinto. He came up with a paper on how to actually convert this Casimir force into a motor, into a cyclic engine, and so he proposed this. And Jordan McClay, he kind of calculated in papers he published for the NASA Breakthrough Propulsion project, that how much energy can you actually get out of a Casimir thing. Well, Jordan McClay, he came up with this. So if you can kind of have like a negative Casimir effect, you can make a few changes, and these changes are these grooves in the blue sheet. And if you have a certain type of groove, you can convert or reverse the Casimir force and make it repellent. So he was envisioning a little engine with this. So also Morey, he mentioned this very important paper where he kind of shows that you can actually use this zero-point energy and make heat or any usable force out of it without violating any physical laws. So by physics, we are allowed to take it and use it. Here is a calculation table where you can see effective area and smallest separation, and you can see how many joules you can squeeze out of a capacitor like Casimir regime. And you can see that in like the upper left, that's like what we can do today, like 100 nanometer separation. That's quite easy to do. 1 nanometer is pretty difficult, and 1 femtometer is pretty not possible easily. That's like the separation of the size of a nuclei. So anyhow, the upper left is what you can do today, but the joules are not very many. It's not much that you can get out of it. So what we have to do is we have to come to smaller separation and larger areas to actually do something with it. This also is important for us. This is a graph showing how the Casimir force changes if you take temperature and the real metal into account. Real metal means that most, like here in this case, copper and gold, and any other metal, they become transparent if you go to very high frequencies. Like gold is already yellow, copper is already a little red, most metals are grayish, you know, so this is just exactly that curve on the left. So that means that if a field comes to, and the frequency gets smaller and smaller, and the energy of the photon gets higher and higher, they start flying through the metal. If you have like a very high energy photon, it will just fly through the metal. While if it's like a radio frequency, if you have a metal, it will be just repelled like a mirror. Okay? So, and that changing area is just around the visible spectrum. So that's why some metals have a color. So anyhow, that means for us that if you have the higher frequencies, which I told you in the beginning, has more juice, has much more energy in it, well, in that area, the metals are transparent. So even if you get them closer and closer, it won't help you because they're transparent. They're not even there for the photons. On the other hand, temperature helps a little bit and it goes up, meaning there is a lot more photons in this area here, 10 microns. This is a typical infrared region. So if we take into account that we don't have zero temperature, like 0 point energy, if we have temperature, you have more photons, so the effect is more. That is what this graph shows. So one approach would be, this is more like a physical approach, is if we can move away from real metals, if we can go to free electron structures, like plasmas, then you can bring them closer together, you can make smaller separations, and move on in the table to the higher numbers. So this would be one possibility of actually moving in the direction of having a 0 point energy device. So that's why I highlighted these areas. If we get really small, then the energy gets really high. But I think there's another way which is very interesting, and I hope not too far out for this audience, is that there is quite a few evidence that consciousness, that the mind is actually able to influence random processes. Like you can read up in the peer labs and others, they have been studying this. So the thing here is, if we apply this and if we can use the mind to kind of have one region with a little bit more 0 point energy activity and one region with, let's say, 0.1% less activity, it's a much larger number than any electron structure can ever do, okay? 0.1% of the 0 point energy is really a lot of energy. So this is a graph from the peer lab and so forth, and showing that you can change the green line is normal probability. The red line is you've changed it in one direction, and the blue line is you changed in the other direction. So they found out that 0.1% of shifting is quite possible, and like I explained, for us, even much less than 0.1% would still be a large number. Now, how is that? This is the calculation. So I'm already taking very conservative numbers here, because here I'm taking the cutoff frequency is kind of important in this calculation. Means where do you actually stop? I said high frequency, but what is the highest possible frequency? So what I did is I took the 10 to the power 20 eV. This is like cosmic rays that we still observe, high-powered stuff coming from the universe. So, and if you calculate the frequency from that, you come 10 to the power 32 hertz. So I put that into the integral, and then you come 10 to the power 66 joules, which is a lot. And there are other ways of doing it. There's something called the Planck length, so meaning the smallest possible length. It's all debatable where the cutoff is, but definitely 10 to the power 20 EV is observable, so that frequency really exists. And you can see that 0.1% of 5 to the 10 to the 66 is 10 to the 63, so it's still an enormous amount of energy. And that's why I think that this using intention and consciousness is really a key to any of these things. And some people call it the inventor effect, that only when the inventor is there, it will work. Well, actually, here you can see there's something to it. It's possible that this is part of the working of these devices. From the pure physics of it, there's a high likelihood that it is so. So anyhow, this was also mentioned that it's connected with gravity and mass, but that you can take the 0-point energy and actually change gravity with it. This is the next level. And now we come to a few technologies that claim themselves that they are related to 0-point energy, or where I think they are related. Now, if you heard Maury's talk, you already heard a lot about Ken Shoulders and his and his charge cluster. And I personally think that it's very much related to the 0-point energy. It's charges, it's electrons in a small structure running through space, so all ideal for harnessing 0-point energy. And we heard about Myers. These are small discharges. I totally agree with Maury that these discharges are very likely to harness 0-point energy by the whole setup, the whole regime, very likely. So here are pictures from the patents from Myers, and you've heard a lot in Maury's talk. I'm assuming that most of you have heard it. So this is the Rossi device, the cold fusion, for me, very much related. Well, Rossi himself said, like 2 months ago, that he's not really sure what's happening in his device. Well, what you see here is a lot of little boxes, and in the boxes there's a nickel nanopowder, and with certain hydrogen and heat, somehow you get a lot more heat out. So that's called low energy nuclear reactions, or it used to be called cold fusion. For several reasons, people changed the names, and they rather named it chemical assisted nuclear reactions or low energy nuclear reactions, trying to avoid the heavy pounding of the hot fusion things. Okay, only a few more pictures. So anyhow, here's, well, I could tell you how it works, but okay, let's skip that. What can I do? Well, anyhow, these, in the parallel session, you could see the Aquapole device, and in a parallel session next to this session also, you can see how the time waver works, and I think it's very much related. This is the Tesla car, and witnesses of that, and we're working together with his Energy Research Institute and Professor Beck, who's backing up this research and the free energy devices. And Wetzers is also interested in these things. It's in northern Netherlands. And University of Stuttgart is active making devices out of critical Casimir forces. And Paris is working on it. European Union spends a lot of money on Casimir force and how to, you see, nanoscales machines exploiting the Casimir force. So there's actually a big European program to kind of find out how can we make nano machines working with the Casimir force. I skip this. This is what I'm working on right now, trapping ions and doing measurements on single electrons. I'm setting this up in the lab here with magnetic fields and all sorts of things. This is an ion trap that we are building. Here you can see another one was already ready, not made in our lab, and there you can store single ions. This is a single ion in fluorescence, and you can do very fine-tuned experiments with it, and we hope to actually see what I'm talking about on a single quantum event, not on statistics like the peer people did, but on the single ion. So I'm coming to the end of it. So thank you very much. Well, Sure. I just want to mention that we have the German Space Power Association. We have an info stand outside. If you want more information on our work, you're very welcome to talk to us. So thank you very much.
Thank you so much.
Okay.